Swayam Prabha. Digital India. Educated India.
So this is some background information. So it started in 2011 as in AMPLab at UC Berkeley. It has this concept. So the central concept of Spark is what is called the resilient distributed data sets. Okay, and so it is applicable to both data and computation intensive jobs. It is scalable and fault tolerant. It is integrated with Scala, now also very well integrated with Python, which you will see in the programming assignments. You will use Python, okay, and it has straggler handling, data locality, and ease of use, which are also properties of MapReduce. Okay, so it has all these properties. The main, so we will come to that, okay, and it so pretty much has the same setup in terms of computation as MapReduce, works on a cluster, and at the back end is a distributed file system, okay, and it provides a slightly more powerful abstraction than the simple MapReduce framework for expressing your computation. Okay. So in MapReduce you can only express your extraction, and then so sometimes it's called also ETL, extract, transfer, and load, right. So this kind of logic. So Spark can also express more complex logics. Okay, so we will see some of them. So some of the things that Spark can do, which MapReduce cannot do so easily, are iterative algorithms like machine learning algorithms, okay, and interactive data mining algorithms. Okay. Okay. So so how does it do? Okay. So it does this using abstraction called resilient distributed data sets. Okay. So what are resilient distributed data, or also called RDDs? So what are these? So these are something like, these are immutable distributed collections. Okay. So forget the scalar part for the time being. So these are sets of records. So just like in MapReduce, in HDFS, you view an HDFS location as a set of records. Okay. Similarly, RDD is also a set of records. Okay. But the difference is, so just like in HDFS, the files are immutable or the input records are immutable, so is the case with Scala. So immutability is very important for ensuring fault tolerance. Okay. Immutable means you cannot change them. Okay. But the key difference is that these RDDs are not in the disk, they are distributed in the memory. So sometimes Spark is called a distributed in-memory computation. Okay. So what is the overall framework? The overall framework is that you have these RDDs. RDDs can be, so when you start doing programming in Spark, you start thinking of RDDs as variables. Okay. So you have this RDDs. Okay. You store different things in RDDs, and then from one RDD or using one or two RDDs, you try to compute a third RDD which contains something else that you want to find out. Okay. And similarly you go on. Okay. So this way of generating more RDDs from some existing RDDs is called transformation. Okay. So There are roughly two types of operations in Spark. Okay. First is what is called transformations, which generate. So RDDs are distributed objects in memory. Okay. You have so you have many such RDDs, each of which is distributed in the main memory of all the computers. Okay. And now using let us say one or two of these RDDs, you can generate a third RDD. Okay. This is called transformation. So for example, you can use the map transformation. What the map transformation does is it operates a particular supplied function. Think of it as the mapper function that you provided in case of MapReduce framework. Okay. This function on every record of an RDD. Okay. So this is what the map transformation does. So let's say you have an existing RDD A, you call a map on this RDD with a function f. Okay. So this function f will be applied on every record of the RDD A, and then the resultant RDD B will be created. Okay. Similarly, you can have other transformation like reduce by key. So this is similar to reduce in MapReduce framework. Okay. So your record in this case will be of the form key comma value pair. Okay. And you have a RDD which has records of the form key comma value pair, just like the input record of a reducer in MapReduce framework. Okay. And then this reduce by key operation would would take a function f which operates on a pair of these records with the same key. Okay. And it would produce another record. Okay. There is also a group by key operation which will take all the records with a particular key. Again, it will take a key value RDD, okay, key value pair RDD, okay, and it will group all the records in this whole RDD by that particular key, and then present it as one record. Okay. Then there is filter, which drops, so it will delete a certain set of records from RDD based on a certain condition. So it will be given a function which will evaluate either true or false for a given record. Okay. And if for a given record the function is true, the filter would keep it, otherwise it will just drop it. Okay. Similarly, there is join, okay, which takes two RDDs with key value pairs, and then it performs the join operation. So it takes, so let's say the input RDDs are A and B. So it will take all the records of A and all the records of B with the same key, okay, and it will just create the value 1 and value 2. It will join them and produce another RDD with all these cross product records, as you have seen in the database. Okay. In database you have seen join. So there are different joins, outer, inner join, okay, and all these joins can be done. So these are some of the transformations that you can do. Okay. Similarly, the other class of operations that you can do on RDDs are what are called actions. Okay. So actions are functions or like Spark operations, as you can think, which operate on RDDs, but they produce non-RDDs like simple data structures. Maybe they produce just a variable. Okay. They may produce just one value like one integer, or they may produce an array, or they may produce a very complex object, but they will not produce a RDD which is distributed in memory. They will produce something which is a programming construct, okay, or a programming variable. So if you are using Scala, it will probably produce a Scala object. So, for example, there is the reduce operation which takes in a function which takes two again key value pair RDDs, and it performs operations on the value and produces one output. So, the output could be one value, one number, one vector, anything. Okay? And the reduce will keep applying this, associatively. We will see some examples, and then it will finally produce a vector or a number which is a variable. Okay? Collect will just give all the records in an RDD in one local array. So, that is what the function of the collect is. Okay? Count will just count the number of records in an RDD. Take will take a particular record. So, if you say take 1, take 2, it will take a particular record from the RDD. So, these are some of the now there is, before I go into the other thing, so typically there are two ways of producing RDDs. Okay? So, the first way is what is called using the text file method. Okay? So, the text file method takes in HDFS location or a location on your local hard disk, okay, depending on the file system that you have. Okay? If you have a distributed file system, it will use the distributed location, otherwise it may use a local location, and it will create an RDD. Okay? So, for example, if you read, if you call the text file on HDFS location, it will create one record per line in that HDFS file, okay, or HDFS, the data stored in that HDFS location. Okay. So, this is what the text file does. This is how it creates the RDD. Okay. So, this is many a times the starting point of any Scala program. So, you will see there is some, or any Spark program. So, you will see that there is a Spark context SC which you will get, okay, and then the first line typically will be sc.text file something, because you will want to create the initial RDDs which you will then transform. Okay. The other way of creating RDDs is what is called a parallelize. So, you may give it a data, something like array or something that you have in your program already. Okay. So, and then you can ask the parallelize method, you can pass it to the parallelize method, and it will distribute it among the computers, and it will create a distributed RDD out of this. Okay. So, you can either take it from a distributed file, or you can take it from the program, from a local variable in the program using the parallelize method. So, recap, how do you go from local variables to RDDs? So, if you have to take data from local variables to RDDs, you use the parallelize method. Okay. If you want to do some processing from create some new RDDs from existing RDDs, so your data, your information is there in existing RDDs, you want to create some new information, you use transformations, okay, some sort of transformations. And if you have some data in some RDDs and now you want to get some data back into the local variable like single computer, okay, you use actions. Okay. So, you use some actions. Okay. Now, the key thing here, so all this is fine. Now, the main question that comes to your mind is, okay, so these are immutable things, which means that everything that you, typically when you write C program or all these programs, you override variables, right? So, you override variables, okay. And why do you override variables? You override variables because many a times once you are done processing with the old variable, okay, you don't need it anymore. So, you can just overwrite it with the new result that you have. You cannot do that with RDDs. Okay. So, every time you do any processing, your RDDs are immutable. So, once you create them, okay, they will be there. Okay. So, you have to create a new RDD for storing something else. and this method keeps going on. Okay. So, if it were just done normally, it will be very, very wasteful and you will not be able to do anything. Okay. So, then comes this concept of what is called the computation graph, and then task list and execution. So, once you provide your logic using these three things, so you create the RDDs, you use transformations, and then you use your actions to get the final results. You provide your logic like this, thinking that you are creating new variables, but all these RDDs will be materialized on demand. That means the RDDs are only existing logically when you provide these RDDs. So, when you provide this entire program or Spark program that you write, so you can your Spark program is not like your MapReduce program. Okay, so it is very, very well integrated with a programming language. So, you can have a lot of the logic that you have in that general purpose programming language, which was not available in the MapReduce program. Okay. So, you write your program, and the big data part you write using RDDs and the transformations and everything. Okay. The Spark engine will optimize the execution of this program. If there are some unnecessary RDDs, it will not even create them. Okay. So, if there are, let us say, RDDs which you define but never use, it will not even create them. If it figures out that a particular RDD is no longer needed, it will be sort of deallocated. Okay. So, there will not be any memory. Okay. In fact, it creates what is called an execution graph of the entire program, and then it actually works out the dependencies. Okay. So, this execution is highly optimized. Okay. And what this means is that basically and the other thing is that it takes care of co-location. So, when it creates this execution graph, okay, so it first creates the execution graph, and then it creates the stages and in what order things should be executed, different tasks or different transformations should be executed. Okay. When it does so, it also keeps track of how to take care of fault tolerance and all these things. Okay. And if a particular node in this execution graph fails, okay, which is also sometimes called the lineage graph, we will see some example of this. Okay. It knows how to restart that. So, it knows which nodes in the execution graph depends on which other nodes, which other data. So, which RDD depends on which other RDDs, and if a particular RDD fails, it knows how to recreate this. So, it has the execution, and once it knows that it has all the downstream RDDs, it can then let go or deallocate the previous RDDs. Okay. So it knows that it will not need to have the previous RDDs. Okay. In fact, it is slightly more complicated. We will go there. And then the thing is, you can also, so sometimes your RDDs can fill up all the memory. So, you can also cache some RDDs. Okay. So, you can store some RDDs, and if they start filling up all the memory of the cluster, you can also store them into disks. So, there is a graceful degradation also. Okay. And the Spark framework recomputes the loss splits of the RDD. So, it takes care of fault tolerance in this manner. Okay. So, RDD is an immutable partitioned logical collection of records, and it need not, as I discussed, need not be materialized, but contains information about how to build the data set. So, the RDD basically. Okay, we have discussed this. let us see this example of again. So so this is a task of mining error logs. Okay, so you have, let's say, some logs, some web server logs, and you want to see what are the errors your web server was throwing. Okay, so as previously shown or previously discussed, typically your you know your execution or your what should I say, your Spark program should start with a text file. So basically the text file command will create the first RDD. Okay, so so the first sentence or the first text file command here is creating the RDD. Then there is a filter transformation on that. Okay, so filter takes every record. So underscore in Scala means means the current record. So it is one way of providing the the function or the so filter, map, all these transformations, they take in as input a function, right? A function in that programming language. So this is the function. So function says take as input the current record, which is a string in this case, okay, and dot contains is a kind of a Java or a Scala method which returns true if it contains the string that is passed. Okay, and the string in this case is error. So if this string contains the input, the record string contains the string error, then it will return true, otherwise it will return false. So it will first retain all the records which have error. Okay. So that is the first RDD that is created. Okay. So then the second RDD, so that RDD is passed through a map transformation. The map transformation then splits it into two parts or splits it into many parts using the tab operator, and then it takes the second part. So maybe that contains the error message. Okay. Maybe the first part contains the error, and then it stores it in a cache. Okay. And this is an RDD. So this will contain basically all the error messages that are generated by this particular web server log. And below what you see is the lineage graph for this. Okay. So first is the HDFS RDD, then there is the filtered RDD, then there is the mapped RDD, and then there is cached RDD. Remember that right now nothing has been done. So there is no data processing that has been done, only this graph has been generated. Okay, so this is very important. So if you give this command in Spark, you will see that it will take fraction of a second to execute, even if you have a terabytes of file. That is because it has not done anything, it has just created this lineage graph. Okay. Why? Yeah, so it is taking probably the second part of the, so split returns array of strings. So this split function, so you are saying why there is a 2 within bracket here. Okay. So split returns array, okay, which yeah, but maybe there is no tab in between, so it is splitting only on tab. So the assumption is that there is no tab in between. Okay, so the question is clear to everybody. So what he is saying is, it may so happen that the second part also contains tabs, and then it's a very big string, and then there is a third part and fourth part and fifth part. In which case, yes, it will miss the other parts, but maybe there is no tab, or you can replace the tab with some other delimiter. Clear? Okay. So now let us see the architecture of the a typical Spark program. Okay. So A typical Spark program will start with what is called a Spark context. Okay? Yeah, so the starting point to a Spark program is a Spark context. Okay? So this has all the information about the Spark cluster. Okay? So what are the components? You remember we discussed the components of a Hadoop cluster. So what are the components? The components is a file system. So there should be a distributed file system, and there should be a resource manager yarn. Okay? So the Spark context will have sort of information about both of these. Okay? So, or in other words, the cluster manager. Okay? And now what it will do first is it will start what is called a drive, or it will start. So when you run a Spark program, first what is started is the driver program. Now what is the driver program? So the driver program is nothing but a local program in the machine where you have fired this command. Okay? So remember that the Spark is very well integrated with a programming language. So suppose you are writing this program in Scala, it is nothing but, so the driver program is nothing but a simple Scala program which is running probably in a JVM in some machine. Okay? But it has reference to this Spark context, okay, which in turn can create connections to this cluster manager. Okay? And then it does all the things. Okay? So when you start executing all these Spark commands, okay, it first creates the graph, okay, and then when it sees some action, okay, it will try to execute that action. Okay? So then it will request the cluster manager. Okay? The cluster manager will create these worker nodes in an appropriate place. Okay? And these worker nodes will then execute this part of the data graph. Okay? And then that particular Spark program will be executed. Okay? So this is typically the architecture of a Spark program.